So, as I used to say every evening to Ajit, we are almost there. We started 9 days ago, non-stop, and I think we just have, yes, we'll cross the line in a few minutes. It was not meant to be a presentation, so it's just a few notes for me at the very beginning. I took 2 weeks ago because it was just the idea, perhaps if I have time before the conclusion of the conference, perhaps I will have the occasion just to show how to use BayesiaLab to try to implement or to go from practice to practical research, right? After the talk of Judea and the course of Felix, right? And so I started reading this book, Causality, and I think most specifically this article. So I don't know if you have read this article, but it's a really good one. Perhaps it's too small for you to see. So I guess Yuda will send it to you because he wants the mailing list, so he will have it. And this is a really good one, easy to read, and that allows to really make the connection with path diagram, structural equation models, and then with BayesiaLab at the end of the day, right? These cheerleaders. And so the thing, yes, I will not speak during 1 hour. It's just a few, not a few tricks, but a few illustrations how you can use BayesiaLab for computing, standard direct effect, and so on. So yes, just let's start with that. So here, so I will really use their vocabulary. So you will not have any context. So it's just X, Y, Z. So this is really the kind of variables they are using every day. So not really exciting, but well. So for those who went to, how many of you went to the Felix course? Anyway? Oh, half. So U here stands for unobserved, and then X, Z are usually treatment and pretreatment or confounder, and Y is usually the outcome, right? So here is a path diagram, and you have 4 variables and then 4 coefficients. And in this world, as the name of the article indicates, we are just focusing on linear models. So this is easy to understand. But then, even if it's easy, this is really nice to illustrate things, right? And we don't have any error term. So this is really a kind of caricature, but I think this is nice to explain. And so in this path diagram, we have U connected to X, and it's a causal link. So we know that there is a coefficient of 0.8 between U and X, another link between X and Z, Z and Y, but in conjunction with U, right? And if we focus on this, these parameters are called the path coefficient, or the structural parameters, right? And they do carry causal information. So this is not just association here, right? And here, when we are focusing just on one of these parameters, so I'm here on A, as you can see, A stands for what would happen to Z if we are just raising by 1 unit A while X, while keeping all these other variables constant, right? And here we are really in a pure linear system. So all these variables are between 0 and 1. Everything is linear, right? So this is the meaning of A, of this coefficient. And when you have a look at this path diagram, at the end of the day, we have a linear structural equation model. So we have X equal Cu, Z Ax, and Y equal to Bz plus Du. And this is not a set of equations like that. This is really affectation here. So you cannot just say, oh, okay, we'll reverse and compute X or U with X, right? So this is prohibited to do that, okay? So we have this set of equations, and just again for vocabulary purposes, X is called the dependent variable, and U, in this case, is the independent explanatory variable. And again, this is non-symmetrical, right? You cannot reverse the equations. And here is the first link with the BayesiaLab vocabulary, if you will. So we have the structural parameters here correspond indeed to the standardized direct effect that we have in BayesiaLab and that are associated to each child, right? So in this case, linear system, we have these standardized direct effects. And then, how do we estimate this direct effect? We just now assume that all the graphs you will see now, so as you can see, these are Bayesian network, are causal graph, which is a strong assumption that I'm never using usually, right? So, but here, everything you are seeing is causal, right? And if we have this graph, x is a direct cause of y, and y is the cause of x, of z, sorry, with the coefficient a 0.9 and b 0.8. In order to estimate the direct effect of x on y, we should not control the descendants of y, right? So if we do if we condition on z, or if we control, we will bias the estimation of the direct effect of x on y. And when I say if we condition, if you remember, Felix described how, I don't remember how many ways you were available for conditioning. It can be just a selection of a subset of points. It can be a statistical conditioning. It can be matching. It can be lots of things just to condition, right? Even if you are just selecting a subset of game, for example, for the football, right? So there is a problem if you do that. And then in BayesiaLab, let's suppose you have this causal graph. You want to estimate what is the direct effect of x on y. You are looking for, indeed, to the value of a here. That is given, but we want BayesiaLab to compute it. So you have to define z as a non-confounder. So this is a way we are indicating to BayesiaLab that please do not control this variable, right? So you you just select z, right-click, class editor, and associate this node to the class, a predefined class, non-confounder. So this is the technical way to do that. And if you do that and use the direct effect function, you will have the correct standardized direct effect, which is here in this case the same thing as a direct effect, as we have something uniformly distributed and between 0 and 1. Then, if we want here if we are not careful enough and we are not defining z as a non-confounder, so if we control it, because when we compute direct effect within BayesiaLab, what we do is we are increasing by 1 unit the driver we are analyzing, x, while holding fixed all the other node, which means that we are using likelihood matching in order to prevent any movement in the probability distribution of z. So if we do that, you can see that the result of a is not anymore 0.9, but 0.67, right? And this is, you can think about a physical system. We are just here applying a constraint, right? So we are trying to move something from x to y, but still here, we are still holding something, right? So it's not working. So we have a bias here, right? So be careful, never condition on a descendant of your driver. Here, in this case, I'm now focusing on z, right? So I'm not focusing on y anymore. And if I want to estimate the direct effect of y on z, so if I want to find b here, I don't care. I can control x or not, right? So controlling x will not have any bias on my estimation of b, right? So even if we can sounds counterintuitive, I am not applying any constraint on y by just fixing x, even if it's deterministic. Well, with likelihood matching, it will be perhaps a problem if it's deterministic, but if it's almost deterministic, it will be okay. And then here, I have x not defined as a confounder, and still I'm able to estimate b, right? This one, I want to estimate the direct effect of y on z, right? This one, b. And I still, I have to define, I do not have to define, sorry, py, which is a proxy of y, as a non-confounder. Right? So if I control, you see something? So if I control py, I will not bias my estimation of b, because it's not on the path. Right? Remember this. If now I have some intermediaries, right? So I want to focus on, I'm still focusing on z here, and I want to estimate the direct effect between brackets because it will be mediated via y. I want to see the effect, the causal effect of x on z. I do not have to condition on the path, right? So if I condition on y, I will obviously cut the information flow, and then I will not have any effect of x on z, right? So in that you can see, if I do not set y as a non-confounder, the information will be absolutely absorbed, and then I have a zero direct effect, right? If I'm setting y as a non-confounder, but still I'm controlling py, which is a proxy of y, I will also have a bias. It will be smaller, but I will have a bias. It's smaller unless py is a perfect clone of y. If it's a perfect clone, I will also remove all the information. But the stronger the relation between y and py is, the bigger the bias will be, right? And then you will see here that my standardized direct effect is not correct. So it's almost the same structure, except that this time I reverse the link py, y. So it's not anymore proxy, so it's more y that is a proxy of py. In this case, I can control py. Or not, we don't care, right? There is no information flow here. So it will, the estimation of the direct effect will not be biased, given that I am not controlling y, right? And here is the case. So now we will just talk about this right path tracking for computing standardized total effect, and I think this is really nice stuff, this right work. So here we still have our network, u, x, z, and y, and we want to compute the total effect here, not only the direct effect, but the total effect. So here the total effect between u and x is given by just c. Right? So the information is going from u to x directly, and we know that the parameter, the structural parameter is equal to 0.8, and that's it, because there is no, now I think you are used to that, you have done so many exercises with Felix, the information is blocked here by y. Right? There is a collider here, so the information cannot go from the only one open path from u to x. This is ux. We cannot go from x, z, y, because here y block the information. Right? Then there is another one. If we want to compute what is the standardized total effect of x on z, this is just equal to a, for the exact same reason. I have the link x, z, and then this is the only path, because this one is again blocked by y. Okay? Good. Some energy. So now let's see how we can compute the standardized total effect, direct effect, sorry, of z on y. So this one. So it will be equal to b, right? Plus we have a path here from z to x and x to u plus u y. So the STE of z to y will be equal to b plus the product of these three coefficients, a times c times d. Right? And here we can see that this is not causal. So the red arrows here, as I said, we are dealing with a causal graph, right? So the link xz is not the same as zx. So we are not here going in the causal direction. We have another one here, uy. It's the direct effect of uy, d, which is d, sorry. And then we have another one, another path, ux, xz, zy. So the final value of the standardized direct total effect of u on y is just equal to d plus the product CAB. And this one is causal, right? So the thing is, in this very simple case where everything is linear, these coefficients are indeed exactly the same one as a Pearson correlation, right? So you can use the direct effect or Pearson here, you will have the same thing. Or the standardized total effect, sorry. So which is the reason why it's not causal, right? And then if we want to have the standardized total effect of z on y, we have to block the backdoor path, right? So we need to really condition, we need to either control x or u. Okay, just to be sure that we don't have any information coming from z via x or u. Okay. So this was an illustration of the backdoor criteria, quite easy now. And here it's, I don't remember, I don't think Felix talked about the front door, did not have the time for that. This one is slightly more complicated. So we have here, still, suppose we have u as, which is really an unobserved variable, right? And we still have the same coefficient. If we have a data set that describes this universe, right? We just have three available variables, x, z, and y, right? Because u is unobserved. So if we have a data set with that, we will learn a relationship and then we'll find a link between x and y. And here I did it on purpose. We will not be able to detect any direction for this link, right? And it will be a spurious direct relation between these two variables. And the value, if we use the right algorithm, the value of this direct effect will be equal to c times d. Right? So the two coefficients we had between ux and uy. So we know that for sure you can take this network, generate data, and you will find that if you exclude u, as I did, you will have this link with this exact same standardized total effect, direct effect. And so this is what I just said. And we know that if we have this causal graph, the true direct effect is indeed defined as the product of A and B. We know that for sure. This is a rule, right? So we know that the true one is equal to 0.6, which is not the same thing as this 0.1, right? So this is something interesting. And if I reverse the link between x and u here, now I have a causal effect which is different because I have two paths, right? And then the correct standardized direct effect here will be given by the product between A and B plus CD, right? So this will be the standardized total effect. These two paths, right? If this link is in this direction, right? So this is the example Julia took. So this is coming from the book, Causality, and is using this example in order to illustrate the front door criteria based on, so this is a pure artificial data set, right? And we have these relations. So we have x is equal to smoker, z to tar, and y is cancer. And there is a hidden variable there that we will talk about in a few minutes. But let's suppose that we just have this. We have a data set describing these three variables. We find a link between smoking and tar. So the more you smoke, the more tar you have in your lung, right? And this link is strong, 0.9, right? And then there is a link from tar to cancer, and it appears that this link has a slightly negative relation with cancer. And we have a very strong link to here between smoking and cancer. And the coefficient is 0.72. And this is the common wisdom. If you smoke, you are increasing the risk of cancer, right? But here, so the direct effect is highly positive. And what the tobacco industry is just telling, just to try to say, no, there is no problem, indeed. They are just speculating that there is a hidden cause here, above the U variable here. This is a genotype, right? So you have some genes. And if you have these genes, so by birth, the first time you will smoke, you will probably like that, right? So you will increase the priority to smoke. And this is indeed the explanation between smoking and cancer. But there is no direct link between smoking and cancer. And they even claim that this is a contrary. Because if you have this gene, and if you smoke, you will increase the tar in your lung, and then you have this negative effect, and you will reduce the probability of cancer. Okay? And if this model is indeed the truth, they are right? And for this, you have to use a nice formula coming from UDA, or if you want, you can also use BayesiaLab. It's more easy. And for that, this one. So we have this information, the positive relation between smoking and tar, negative relation between tar and cancer. And we have here, this is a true effect. If we use the right rules, we have a negative direct effect of the product between A and B. So something strongly positive multiplied by something slightly negative. So we have a negative direct effect between smoking and cancer. So using the theory, they are absolutely right. Okay? Let's have a cigarette, if you will, just after this talk. And if we want to do that, so there is the formula is described in the book. So you have to intervene on smoker and then take the marginal of, or take the conditional of tar given that you are smoking, and then take the marginal of smoker, blah, blah, blah. So this is not a complicated formula, but it's not so easy either. And so if you want to be able to retrieve this direct effect in BayesiaLab, you have to manually add the hidden node in the network. So you just have to create this node. So those who use BayesiaLab now know that this node will be white, right? You have to add a link from this hidden node to cancer, and then, it was my question a long time ago, I say, but what would be the conditional priority here between this hidden variable and cancer? And indeed, it's quite easy, because we just have to take the one coming from cancer from smoking to cancer. We replace this one, and then we don't care from the link from U or from gene to cancer, to smoker, sorry, we don't care about this priority dispersion indeed, because as we will intervene, we'll remove this link, right? And then we have this direct effect. So it's not difficult at all. If we know that there is a hidden variable, so if we have some expert knowledge, we'll be able to directly use BayesiaLab for computing this from-door formula. So we can either use intervention, or we can use, so likelihood matching, and then we need to use direct effect analysis, or we can set the node smoking as an intervention and use then the total effect, as we are going to remove the link from smoking to the hidden variable. So you just make a right click on the monitor and say smoking is not now just a node that I will observe, but I will intervene on it. So I will make the do operator. And then we have the same result with the total effect, right? And you have this small arrow associated to smoking, just to let you know, to remind you that the analysis you have done was done with the intervention operator. Okay? So here, a few words about the difference between likelihood matching and intervention. So the way we are doing likelihood matching is we have implemented a kind of dynamic Jouffe rule here in order to have, so the original idea was to have a probability distribution. You have to compute a likelihood distribution. So we have an algorithm that you are just specifying the distribution you want, and then given the prior we have, we compute the likelihood distribution that allows you to get this final probability distribution. So this is a static likelihood. And the dynamic one is just to say, given that we have some new evidence, we will dynamically update this likelihood in order to still have the same probability distribution. And likelihood matching is even easier. Based on this, we just say, oh, I want this probability distribution to be held constant, and then I want, each time I'm changing something, I'm simulating this plus 1 unit, I want my control variable to keep the exact same distribution. So this is the way we are doing causal analysis here. Right? With the intervention, so there was the work of Udea, the idea for making the independency between your decision and one confounder is to remove the link. And you can quickly understand why this is working, because by removing the links that are directly connected to your action, you are removing the backdoor, right? So we are just mutilating the graph, and then we have the direct effect of our action. But, well, we'll see later. So likelihood matching, there is one advantage with respect to intervention. This is that we don't really need to have a causal graph. So we don't care about the direction of the links. If I have some time, I will show you an example. But it works, any direction will work, right? Whereas with the intervention, as I said, we are mutilating the graph in order to implement the backdoor criteria. So in order to define the backdoor criteria, we need to know what are the incoming links. And if the link is X, Y, or YX, it will not be the same consequence, right? So this is really working only on the causal BBN. So you have to be sure that your links are in the correct direction. And the problem, I still do not have the answer, we can have slightly different results. So this is almost part of the advanced course, right? So we have this very simple graph here, where U is connected to X, X to Y, and I have a uniform distribution on U, uniform distribution on X, and then a uniform distribution on Y on this very simple graph, right? And if I use likelihood matching, if I use likelihood matching to compute the direct effect of X on Y, I will have a value equal to 0.64, which is almost the same thing as the one with intervention. But there is this almost there. And the thing is, when I'm computing likelihood matching, or direct effect with likelihood matching, I'm just fixing the probability distribution of U. So let's suppose I want to test what is the direct effect, not of what we call a hard intervention, but with a soft intervention. So I don't want just to say, I will make these guys smoke, but I will take 50% of the population and then I will make them smoke, right? So here I'm just saying, what if I'm doing something with 50% true and 50% false? So it's a soft intervention. If I do that on this model on the left, the result is 0, because I'm just doing the same thing as what I've observed, right? But if I intervene with this soft intervention, I already have an impact here, even if nothing has changed on x and y, on x and u, sorry. I can see that I already have this minus 0,2. And this is just due to the mutilation. So removing the link between u and x, I'm already not representing the same joint. So even if in my mind, at least naively, I'm thinking I'm not doing anything different from what I have observed before, I already have an impact. So I had a long discussion with Judea on this, but we still do not have the answer. I don't know where is the truth here. I have one idea, and I think I think the intervention should be correct, but who knows? Perhaps not. And then here is a curve. So as you can see, it's not different. There is not a huge difference between the two. And at the end of the day, for hard intervention, this is exactly the same result. This is just for soft intervention. And the reason why I think Judea is right is that with intervention, so you still have a linear slope, which is not the case with the likelihood matching, where we have a small slope. Okay. And just to conclude, here is an example that Felix sent me just 2 days before his training. He wanted just to know if it was possible to handle this kind of graph with BayesiaLab, where here we have two direct action, two drivers, x1 and x2. So these are drivers that the company can directly use, right? And there is another cause, z, that in this is not directly controllable, but it's a cause. Right? And so the company, if you take the action to do x1, you will have the direct effect of x1 on y, and you have the total effect via z. Right? So there is indeed, if you change the value of x1, you will have two paths to improve your target. So for right now, it's not a problem, right? But when you will estimate, if you don't want to have the bias of controlling a descendant, you have to set x2 as a non-confounder, right? No, sorry. You need to set z as a non-confounder, right? And then you will have the path. But as you have to control for x2, if you just want to have the direct effect of, or the effect of x1, you will bias because you will control the descendant of one of the nodes on the path. Right? So we will not be able, by using likelihood matching, for this example, we cannot estimate x1 or the direct effect of x1 and even the one of x2. So for being able to do that, we need to use a conjunction. We need to use a conjunction. We need to use both likelihood matching and intervention, or the two intervention if we are sure that all the direction of the links are correct. But in order to solve this problem, you just have to say, okay, x2 is indeed an intervention, and then when we don't have to define it as a non-confounder, we don't have to condition on it, and then we will not have this bias. It will just remove this link. Okay? So we have two biases. And so if we do that by using, by setting, so this is a result if we are biasing, and setting x2 as an intervention, then we are able to find the correct effect. And you can check these effects are you just have to use the right rules in order to make the product and compute the effect of the path. So here it's 0.5 plus 0.8 plus time 0.1, and this one is these two paths. Only one, sorry. 0.2. So, on that, either it's crystal clear, and I think it is, right? And I still have 5 minutes just to make, or not. It's your call. Do you want to see the Just the illustration of this likelihood matching and causal analysis, or not, or you are done. So let's use Beaky for a rapid, a quick survey. So, what time is it? 5:45. That's this one. So I will use this one. So I think this is. Everybody knows about the Simpson Paradox, right? So the Simpson Paradox, this is this very classical example. So we have the treatment, the confounder is gender, and we have the efficiency of the treatment, the outcome of the treatment. So if we naively want to compute what is the effect of treatment on recovery, let's assume even that we don't have this. Let's suppose we have a study and we just have treatment and recovery, right? This is based on the observational data. We will just compute what is the difference of treatment equal false and treatment equal true. So we can see, oh, treatment allows me to increase by 10% the chance of recovery. So if I'm the public health ministry, I receive this kind of result, I say, okay, we need to do that. Everybody need to, all these people that are sick need to take this treatment. This will increase by 10% their chance of recovery, right? But here there is this confounder, and if I set treatment equal true or false, I have a strong impact on gender, just because these guys did not select the treatment randomly, right? It was not a controlled experiment. They just used their free will for choosing the treatment, and it appears that because of some adverse side effects, women did not take the treatment, or were not less likely to take the treatment than men, right? And then focusing on people who did not take the treatment, then we are mainly focusing on women, and those who took it, mainly focusing on men, and it appears that men are less likely to die than women in this small example. So focusing on treatment only without being careful about sex gave a very bad result. So if I want now, I need to mutilate the graph. So this is the way UDA is doing it, right? So this is, we have the same graph with recovery, treatment, and sex, and in order to control gender here, we just have to remove the link, and now if I compare true and false, I have for false 50% of chance to recover, and if I take the treatment, 40%. So this is reverse. Before it was plus 10%, now it's minus 10%. So it's a very bad decision to take this treatment, right? So this is the way to do that. Another way, and this is a kind of old-fashioned way, is indeed, because deleting the link in a network, well, it's kind of funny when you have 3 nodes, but when you have lots of nodes, it just, you cannot do it, right? So another way is just to add another node here, do treatment, right? And this node has 3 states, one for epsilon, another one for true, and another one for false. And it's a direct parent of your action, right? Which is here. And this, if I set true, you can see that treatment equal to true, and that does not change sex. So, very quick question for you guys. Is it obvious why it does not change sex? Even if now I said the same thing, I said 100% on treatment.
You created a special CPT there?
Oh, you know, it's a classical one. This is just the if, oops. Where is mine? No, where it is. I close it? Okay. You have the time to think about it. So it was here, the CPT is this one. So we are looking if it's, not this one, sorry. Not on the right node. So if it's true, If do treatment is true, then it's true for treatment. If do treatment is false, then it's false for treatment. And if I don't know, I'm just taking the exactly same probability distribution. So here, what was the... Mike, you had an idea. No? Yes. I thought you so do you know why, if I do that? True?
Oh, because of the collider.
So in this case, it's a really counterintuitive one, because we are really setting 100% on this one. And even though we don't have this connection. Right? It's kind of funny. This is an extreme case of the collider. So this is one way to do it, and it's not really more easy than removing the link, because if you have a network with 50 nodes, you will have to create 50 new nodes with these additional links. So the way we did it, we can do here set treatment as an intervention, right? And then if I do treatment, I'm removing the link, right? If I don't do anything, and the difference with likelihood matching is even if I don't do anything here, I'm removing the link, right? And so the other way is likelihood matching. So, and here I did it on purpose, you see. My network is absolutely reverse here. I don't have any link in the right order. But still, if I say I want to control gender, 40, 50, so I have the exact same result. So in this case, I don't care about having a causal graph. What I care about is I need to know which node I need to control and which node I don't have to control in order to not introduce over-controlling bias or these kind of biases. So this will be my final remark. And